Okay, this is a mathematical supplement to my talk on gravity as a force. I'm going to try and summarise the mathematics as best I can. This is basically going to be general relativity on a single page of A4 in under 10 minutes. So let's have a go. Before I start, I need to do a few notational conventions. We will use the Einstein summation convention. So if we have A dot B, two vectors, and we do it by summing the components, A1 B1 plus A2 B2 dot dot dot, that's just written as A I B I. So whenever you get an index that appears in both an upper and a lower index, the summation is implied. The other thing we're going to do is that very often we need to do d by dt, d by dx, d by dy and d by dz. We need to apply all four of these to vectors. We'll write that as d by dx nu, wherever we use a Greek index it means all four of these basically, and we shorten that even further and we just write d nu. General relativity is all about taking a vector and seeing how it transforms as we transport it around curved coordinates. So if we look at our vector components, and this has four components, time, x, y and z, and we see how it changes with respect to all the different components, again time, x, y and z. The vector components are just found by taking the dot product with the basis vectors. Dot products obey the Leibniz rule. All I've done here is rearrange the components to put this on one side by itself and these two on the same side. What we do now is we rename some of these. This has got an upper and a lower index. We change that and define that to be capital D nu V nu. Now this is called the covariant derivative. It includes two parts. It includes the derivative of the components of the vector, but it also includes the derivative of the coordinates. So it's taking account of the way the vector changes, both with the vector itself changing and with the coordinate system changing. We won't use the covariant derivative too much in the rest of this talk, but it becomes very important in future talks. It becomes especially important when we discuss the weak force and the Higgs mechanism. This is a dot product between the vector v and this thing, the derivatives of the coordinates. We give these a special name as well. We call these Christoffel symbols. And they get the letter capital gamma. The extra index here is a dummy index. It's just the summation that we need in order to take the dot product of these two, and that should be a plus sign. We define it in terms of their negative. This is the interesting bit. This is the way the coordinates are changing. It's what I called a local transformation in my other video. Essentially, this is gravity. I need to introduce something called the metric tensor. Now the metric tensor is just a block of 16 numbers which tells you how to add up components to measure distances. For special relativity it has the values -1, +1, +1, +1 and 0 everywhere else, and it basically just says that the way that you measure distances in special relativity is c dt squared with a minus sign plus x squared plus y squared plus z squared. It's defined as the dot product of two basis vectors. And since we know how to do covariant derivatives, we can apply them to the dot product, and what we find is that the covariant derivative of the metric is always 0. This allows us to define the Christoffel symbols in terms of the metric and the derivatives of the metric. So we've got some notation for describing changes in coordinates, and we've got some notation for measuring distances. The next thing we need is something to describe curvature. Now, the way we describe curvature is we take a vector and we move it around a small loop on a surface. And if there's curvature present, what happens to the vector is it changes. We find that we get a small change in the coordinates of the vector. Now we represent a general area in space-time by a small tensor. It has to have two indices because there's two dimensions here, so call them lambda and rho. So what we have is a change in a vector, and it's going to depend on the vector itself. It's going to depend on the area that we transport it round. And to match up all these indices, in these type of equations, all the indices have to match up. We're going to need this tensor, which needs to have that index there. And it has to match up with all these indexes here as well. So this is a tensor. Each of these indices has 4 components. It's got 4 indexes. So this is a tensor with 256 components, and it's called the Riemann curvature tensor. But we know how the coordinates vary in terms of the Christoffel symbols. So we can actually do this calculation. We can take the vector and see how it changes as it goes around. And we find that the Riemann curvature tensor can be expressed in terms of the Christoffel symbols and its derivatives in this ugly, complicated expression, which is itself, remember that each one of these can also be expressed in terms of the metric and its derivatives. Now, although there's 256 components in this tensor, the Riemann curvature tensor actually has a lot of redundancy. So we define a thing called the Ricci tensor, or maybe it's Ricci tensor. We set these two components to be equal and sum over them. This is the equivalent of taking the trace of a matrix or the length of a vector. Most of it is simply eliminating redundant information. We can actually go one step further and actually sum over these two indices as well. This is called the Ricci scalar. Now these two measures of curvature, the Ricci tensor and the Ricci scalar, have an important property. If you combine them like this, and then you take their covariant derivative, the result is 0. What this is saying is that this measure of curvature remains the same even under a change of coordinate system. That's exactly what we would like to see in our laws of physics. Now the 0, 0 component of this tensor refers to time and energy, which is the same thing as mass. But we already have an expression for mass density if we express Newton's law as a field equation. This is the mass density, this is the gravitational potential. So if we assume that this curvature is our gravitational field, then the thing on the right hand side must be a 16 component object whose 0, 0 component is the mass density. We call that tensor the stress energy tensor. Its 0, 0 component is mass and energy. The 1, 1, 2, 2, 3, 3 components are momentum, and the other components are the flows of energy and momentum in various directions. And if we want the constant of proportionality to be correct, we find the following. This is Einstein's field equation. It's a set of 16 simultaneous differential equations. On the right hand side we have energy, mass, momentum, and the various flows, pressures. On the left hand side we have curvature, expressed in terms of the way that the coordinates change, which in turn is expressed in terms of the metric, the way that we measure distances. And if you take the 0, 0 components of these two tensors, and you take the case where energies and velocities are non-relativistic, so speeds are very much less than the speed of light, you get this field equation, which is really just Newton's law for gravity. So there we have it, General Relativity in less than a page of A4. Didn't quite make it in under 10 minutes.